Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210 Introduction to the Sky and Solar System, Lecture 6, As the World Turns. In this lecture, we're going to examine how our view of the sky changes during the course of a day as the Earth spins. So, first of all, just a quick reminder, the Earth is rotating around an axis that goes through the North Pole and the South Pole of the Earth. The Earth is rotating from west to east, and it carries us around once every 24 hours. And this rotation of the Earth causes the sun, the moon, the planets, and the stars to move in the sky. Because the Earth is rotating from west to east, the stars, the sun, and the planets appear to move from east to west. They rise in the east, move across the sky, and set in the west. And that's simply because we like to think of ourselves as sitting still. Even though we're the ones that are moving, we don't like to think of ourselves as moving. We think of ourselves as sitting still. And if we think of ourselves sitting still, then the motion in the sky is opposite our motion. Although we are going west to east, it looks to us like the sky is going east to west. Now, just like the sun and the moon, the stars rise in the east and set in the west every day. The stars up there close to the north celestial pole, these are the circumpolar stars. And you can see that during the course of a day, these stars go round and they never rise or set. As we get further and further away from the pole in the sky, then the stars do rise and set. So these stars are clearly rising out of the horizon. They'll move across the sky, and way over on the other side of the sky, they will set. But the stars up here, close to the north celestial pole in the sky, those stars never rise or set, and those are the circumpolar stars. In the northern hemisphere, the stars are circling the pole in a counterclockwise direction. That is, as you face towards the pole, the stars are going counterclockwise. Interestingly, in the southern hemisphere, the stars rotate in the opposite direction. Not because the Earth is spinning differently, but because you have turned yourself around and you're facing the opposite way. And so, for astronomers who live in the northern hemisphere and go to the southern hemisphere or vice versa, it's very odd to look up in the sky and realize that the sky is rotating what appears to be the wrong direction. I've had the great fortune to go down to the southern hemisphere and see the southern sky, and I can tell you it was very disorienting to see the stars moving in what I felt was the wrong way. Again, not because anything is different down there, it's just that from the northern hemisphere to the southern hemisphere, I have flipped myself upside down. I have turned myself around, and that's why the stars rotate backwards. Okay, so there's an image of the circumpolar stars. Here's another image taken from Kitt Peak National Observatory in Tucson, Arizona, again of the North Star Polaris close to the celestial pole in the sky, and the stars circling around the pole. And at different latitudes, the motions of the stars appear different to us. If we were standing on the north pole of the Earth right here, the stars would be circling the north celestial pole, which is straight over our heads. And as the stars circle the north celestial pole, they just go round and round in circles. In fact, what's interesting is standing on the north pole of the Earth, all the stars in the sky are circumpolar because they're circling around the pole. And since the pole is at our zenith, all the stars simply go round and round the sky. They don't get any higher or lower during the course of a day. They just make these giant circles. At the North Pole, and for that matter at the South Pole, all the stars are circumpolar. If you're standing on the Earth's equator, where the north celestial pole is on your horizon, as the stars go round and round, none of them are circumpolar. They all rise, move across the sky, and set. And interestingly, when you live on the equator, when you're standing on the equator, all the stars are up for exactly 12 hours. You can see that the equator cuts the sky exactly in half. And because the north and south poles are on your horizon, and the Earth is spinning around that axis, every single star spends 12 hours above the horizon and 12 hours below the horizon. Here at the North Pole, all the stars are up continuously. None of them rise or set. They are all up 365 days a year. They're up and they never set. And all these stars down here in the southern sky never rise up and you never get to see them. At the equator, on the other hand, you get to see everything in the sky because everything at some point rises above your horizon and then sets in the west. And at intermediate latitudes, like 38 degrees north, where we live here in Charlottesville, we get an intermediate case. Some of the stars here are circumpolar. And in fact, if the north celestial pole is 38 degrees up in the sky, any star that is within 38 degrees of the North Pole will be circumpolar. So you have to be closer than 38. If you're more than 38 degrees from the pole, then you will rise and set. But if you are within 38 degrees of the pole, then you are a circumpolar star. On the other hand, if you are within 38 degrees of the south celestial pole down here, these stars never rise up. We never get to see them. Those are the southern stars, for example, the constellation of the Southern Cross, or lots of other southern constellations like Tucana, the toucan, or Telescopium and Microscopium and Fornax, the chemical furnace. They're all down here in the very far south, which we never get to see. And then at intermediate latitudes right here, or I should say at intermediate, we'll find out in a second, they're called declinations. But in the intermediate part of the sky, the stars rise over here in the east, move across the sky, and set over there in the west. So as an example of a really cool image of what happens at the poles, here's an image taken from the South Pole Station. So at the Amundsen Scott South Pole Station, the National Science Foundation, which is the branch of the U.S. government that funds basic research, they operate an observatory down there called the Martin Pomerantz Observatory. And because they are sitting right at the south pole of the Earth, the south celestial pole is straight overhead. And so if you take one of these star trail images, and this is a full star trail image, you can see the star trails just making giant circles in the sky. Now, another neat thing about the South Pole Observatory is when the sun sets there, it stays below the horizon for 6 months at a time. Interestingly, the South Pole gets 6 months of continuous daylight, followed by 6 months of continuous nighttime. And this photograph was taken during the continuous nighttime, so you get a full 24 hours of rotation of the Earth. And you can see the stars just circling around up there. This particularly bright star here is fascinating because it goes around the sky, never rising or setting. This ghostly green glow that you see, of course, is the aurora australis, the aurora as seen in the southern sky. So those are the star trails over the Martin Pomerantz Observatory at the South Pole Station. So here, oh, and I should have pointed out here, let me go back for a second. You'll notice that there is no bright pole star here in the southern sky. So if you look right at the center of that, you'll see, and in fact, you'll see there are no bright stars anywhere close to the South Pole. And that's what makes the South Celestial Pole so hard to find in the sky. So here we are again at mid-northern latitudes, and so we see our stars circling around the pole, with the pole about halfway up in the sky. So here we are on the big island of Hawaii with the pole, and the big island of Hawaii is at about 20 degrees north, roughly about 20 degrees north latitude. And so that means that the pole is about 20 degrees up in the sky, and we can see the circumpolar stars around it, and then the rest of the stars rising and setting. So now here are two celestial spheres that show us what's happening. And they show you how confusing the motion in the sky can be because of the motion that you're doing. So this celestial sphere is not drawn with the observer straight up and down, but it's drawn as the way that I showed you in that Lecture 5 supplement to begin with the North Pole at the top, the South Pole at the bottom, and the Earth's equator cutting across the middle. So there you are on the Earth. There is your zenith. There is your horizon right there. And what happens during the course of the day is the Earth spins. Your horizon is spinning around in kind of a crazy motion. And what that makes the stars look like is it makes the stars look like they're circling around the sky. And some stars up here are circumpolar. They never rise or set. You'll see they never dip below your horizon. Many of the stars, though, do rise in the east and set in the west over here. These stars rise and set, they go below your horizon, and these stars down here never rise above your horizon. But just looking at this image shows you how confusing it is when we don't put the observer straight up and down. Look at this one for the southern hemisphere. Look at this one over here for the southern hemisphere. Now there's our observer. There's the zenith, the point straight overhead. There's their horizon. And as the Earth turns during the course of the day, what they're doing is they are rotating around the Earth, and this horizon is spinning in sort of a crazy manner. I'll show you a little animation in a minute that clears this up by putting that observer straight up and down. But the first thing is, I want to show you two movies. I want to show you the movie, first of all, on how the sky appears to us. This is a movie taken from the European Southern Observatory in Paranal, Chile. It's taken at a telescope. Astronomers are great at naming things. It's the largest telescope in the world right now, and astronomers gave it the very clever name, the VLT, which stands for the Very Large Telescope. But in any case, let me show you a video of what the night sky looks like down there in Paranal. So let's pause this. Let's go back for a second because there's some interesting things that happen in there that I wanted to point out, but I didn't want to bother it because I think it's such a beautiful scene. But now I'm going to narrate it so as it goes on here. So let me narrate what's going on. So the first thing we see is the Very Large Telescope is actually made up of 4 individual telescopes. Each of those giant telescopes has a mirror inside of them that's 27 feet across from side to side. And the 4 telescopes can work together as one giant telescope. Those streaks that you see running across the sky, those are actually airplanes as they travel through the sky. So you're just seeing airplanes. And now you can see the beautiful Milky Way galaxy up there in the sky. So there is the Milky Way running across the scene with those beautiful dark dust lanes cutting down the middle of the Milky Way. And then you can even see here, that's the Andromeda Galaxy down there. So the Andromeda Galaxy, you'll recall, is the nearest galaxy, the nearest large galaxy to our Milky Way. Oh, I forgot to point out. I forgot to point out in here that you can also see the 2 small companion galaxies to the Milky Way, called the Large and Small Clouds of Magellan. Actually, they're visible in another part of the video. Okay, so that's how the motion of the sky appears to you and me. It looks like the sky is moving. But that's not actually what's going on. What's actually going on is the sky is sitting still and the Earth is rotating. So this next video that I'm going to show to you is how it really is. So they've taken that same video, but now they've changed that video to show us what's really going on. What's really happening is that the sky is sitting still and the Earth is rotating underneath it. So let me just narrate a couple things here real quick. So the first one is that these are the large and small clouds of Magellan, the companion galaxies to our Milky Way. There's another, they're the Magellanic Clouds, again, the large cloud of Magellan and the small cloud of Magellan. In a minute here, you will see some lasers shooting out of the telescopes. I like to joke that those are the lasers that we fire to keep the aliens away. But the truth is that those lasers are actually used to stabilize the images, to cancel out the distortion that our atmosphere introduces. The lasers shine up and hit a layer of sodium atoms high up in the sky, and they make an artificial star. And as that light from that artificial star passes through the telescope, we can see how it's distorted by the atmosphere, and then use that to correct the images. So these telescopes can take images almost as sharp as those taken by the Hubble Space Telescope. Okay, so that is a brief set of movies about what's going on in the sky, how it appears to us, and what's really going on. So to try and make this a little bit more concrete, let me show you a movie, an animation, sorry, is a better way to put this, an animation that shows you what's happening. So I will put this animation in the resources area in Colab. I highly recommend that you play this video over and over and over again until you understand what's going on. So let me narrate the video here. So this is the celestial sphere surrounding us. You can see the stars look like they're painted on the inside of the celestial sphere, just rotating around. Just like we have lines of longitude and latitude on the Earth, we have lines of longitude and latitude in the sky. We call them something a little bit different. We call them right ascension and declination. We'll see both of them a little bit later in this lecture, but that's the lines of declination going north and south, and we saw the lines of right ascension a second ago. So as we scan out a little bit, if we take the North Pole and extend it up, we get the North Celestial Pole. We've got the South Celestial Pole down here at the bottom, and there's the celestial equator. And now we're going to put an observer here on the Earth, and this observer, she's located at basically our same latitude on Earth. She's located at about 38 degrees north. And you'll notice what she does during the course of the day. This is her horizon, and that's what your horizon is doing during the course of the day. And that looks pretty crazy. It's hard to figure out how the sky moves, and so what we think of is ourselves standing straight up and down and sitting still, and it's the sky that's rotating around us. This is what you and I believe. This is what you and I see is going on. We are sitting still. We are not moving, and it is the sky that is rotating around us. In the southern sky, if we look towards the south, we see the stars making these little arcs through the sky. If we look towards the east, we see them coming up at an angle. If we look towards the north, we see the stars circling around the North Celestial Pole up there. There's the Big Dipper, by the way. And then if we look towards the west, we see them setting down at an angle. The stars are making these complicated motions through the sky because of our tilted location on the surface of the Earth. So just to play that last bit of this movie again here for a second. So let's start with our observer here. And just to remind you, she's at the same latitude that we are on Earth. And so this is what you're doing during the course of the day. That is the crazy motion that you make every day. Now this orange plane right here represents your horizon. And that's what your horizon is doing every day. And you can only see the things that are above your horizon. And so it's a lot easier to think of yourself as standing still and not moving, and that it is the sky moving around you. And now you will see why the sky has these odd motions. Here are the stars setting over there in the west, and here's the celestial sphere rotating around us. So just as a quick reminder, in the south, the stars are making these little arcs. Over here in the east, they're rising up at an angle going from lower left to upper right. Here in the northern sky, they're circling round and round the North Star Polaris. And then here in the west, they're going from upper left to lower right as the stars set. So I want you to watch that video. As I said, it's called Celestial Sphere or Cell Sphere 1. It's going to be in the resources area of Colab. Watch that video over and over and over again until you're comfortable with the movements of things in the sky. We can see this in Stellarium as well. So I think it's worth at this moment in time bringing up Stellarium and showing you the motion of the sky in Stellarium. So I'm just working on getting my Stellarium started here. So there we go. There's Stellarium. Let me full screen this here for us. So there is Stellarium. I'm going to zoom out a little bit right here. And I'm going to flatten my horizon so that you can see the stars. So let's speed up the sky and let's see how the stars are moving. So the first thing we want to do, is get rid of the sun there. Let's face towards the north right there. I can get rid of the sun by clicking this little button down here, which gets rid of the daytime sky. So now, even though the sun is in the sky, I can still see the sun, but it doesn't light up the sky. I can still see the stars that are up there in the daytime. So if we face towards the north, the first thing you'll notice is the North Star Polaris sitting up there in the sky. The whole sky is rotating around the North Star Polaris. Here's the Big Dipper, the handle and the bowl of the Dipper, and you can follow those two pointer stars and they point right to the North Star Polaris. You can see how the Big Dipper is circumpolar. It goes round and round the pole and it never really sets below the horizon right there. Skims the horizon but never really sets below the true horizon. So that is what's happening when we're facing north. We see the North Star sitting still at the middle or almost sitting still, and the stars going around it. As we face towards the west over here, we see the stars setting. All the stars are moving from upper left to lower right as they set below the horizon. As we face the southern sky, what we see are stars making little arcs through the sky. They rise over here in the southeast, they move across the sky, and they set in the southwest. If we were to capture a time-lapse image of these for a few seconds, so let me pause this for a second. Look at Spica right here. Imagine that we captured the motion of Spica over a couple hours. We would see that it makes a little arc through the sky. So there is Spica now, and there is Spica a few hours later, so that we'd see that it's making these arcs. What they're doing actually is they're making these arcs is they're circling a point here, and that point is the south celestial pole, which is below the horizon, and we can't see it down there. So that is what's happening when we're facing south. And then, of course, as we face towards the east, turn the motion back on, we see the stars moving from lower left to upper right as they are rising up. So that is the motion of stars in the sky. Not only should you watch that celestial sphere movie that I showed you a second ago, but you should play with the motions of the sky in Stellarium as well. All right, going back to our lecture here for a second. Okay. Now I've reoriented. We did this celestial sphere a minute ago, and it was really kind of confusing when the observer was tilted. Now it makes a little more sense when I put our observer straight up and down, and their horizon is horizontal right here. Now you can see what the stars are doing. Here's the north celestial pole. Everything is circling around the north and south celestial poles. These stars are the circumpolar stars. They are up all the time and never set. Here are stars rising in the east, moving across the sky and setting in the west. This star, for example, rises over here in the east, moves across the sky and sets in the west. This star rises in the southeast, moves across the sky and sets in the southwest. And these stars down here around the south celestial pole never rise up. So to give yourself a little bit of practice, let's take a look at this picture. This is a picture taken from the Very Large Array. I talked about the Very Large Telescope a minute ago. In New Mexico, the United States has built a giant array of radio telescopes. We call it the Very Large Array. What direction was the camera facing in this photograph? So go to Learning Catalytics, and I want you to answer that question. What direction was the camera facing when taking this picture? And the Very Large Array is in Socorro, New Mexico. So it's in the northern hemisphere. What direction was it facing? Okay, so what direction was the camera facing? Well, I can see a bunch of things. I can see all the stars moving, circling around one of the poles in the sky. So this has to be either the north or south celestial pole. There is a moderately bright star there at the center, but most importantly, I know that this is in New Mexico. It's in the northern hemisphere. So this has to be the north celestial pole, which means I am facing due north as this photograph is taken. So this was a photograph taken due north. Let's try it again just for fun. What direction was the camera facing when it took this picture? So this is a picture taken in modern-day Iran, which is, of course, in the northern hemisphere. So again, it's a northern hemisphere picture. Which direction was the camera facing? Okay, this one's a little bit trickier because now the stars are moving lower left to upper right. So It's pretty clear that we're not facing north because we don't see the pole up there in the sky. We're not facing south because we don't see the stars making those little arcs through the sky. The direction we're facing here is either east or west. And the question is, are the stars rising or setting over here? And the answer is, if you watch those movies long enough, if you go to Stellarium and look at stars rising in the east and setting in the west, you will see that these stars must be rising in the east. This is what the stars look like when they're rising in the east. They go from lower left to upper right in the northern hemisphere. So these stars, this camera was facing towards the east. Go to Stellarium, face to the east in the northern hemisphere and face to the west in the northern hemisphere. You can go to Iran to do this, or you can just do it here from Charlottesville. And what you will see is when you're facing east, the stars go from lower left to upper right. But when you're facing west, they go upper left to lower right. So in the west, the stars are coming down literally at a right angle to these stars here. You don't know just based on this photograph whether the stars are going up or down. Doesn't matter. When they are streaked from the lower left to the upper right, you're facing east. And when they're going from the upper left to the lower right, you're facing towards the west. Here's a tricky question. What direction was the camera facing when taking this picture? This is at Cerro Inter-American Observatory down in Chile. So which direction was the camera facing when this picture was taken? So take a second to answer that question. All right, this one was tricky because this one was taken down in the southern hemisphere. And so you can see the stars, they're all circling around the south celestial pole, which is up here off the left-hand side. And in the southern hemisphere, the stars are going in a clockwise direction, which means these stars are setting down here. In this case, they're going from the upper right to the lower left. And these stars happen to be setting. And that's because, again, in the southern hemisphere, you have flipped yourself around. So in this case, when we see the streaks going from lower left to upper right or upper right to lower left in the northern hemisphere, this is facing towards the east. But in the southern hemisphere, that's facing towards the west. So that's a little bit about how the stars move through the sky. I do want to take a moment now to talk about celestial coordinates, a completely different topic. But I felt this was a good time to talk about it because I said before that altitude and azimuth are not a great way to measure the positions of stars in the sky because they're constantly changing. It's how we see the sky, but I can't call up another astronomer somewhere else in the world and tell them to look at an object that has an altitude of 30 degrees and an azimuth of 70 degrees because that object will have a different altitude and azimuth for them. So astronomers have a celestial coordinate system that is just like the lines of longitude and latitude on Earth, but we call them right ascension and declination. So these celestial coordinates, declination is your north-south position of a star on the celestial sphere. It is exactly the same as latitude on Earth. And just like latitude on Earth is measured from the equator, where the equator is defined to have a latitude of 0 degrees, in celestial coordinates, declination is defined on the equator, celestial equator, to have a declination of 0 degrees. So the celestial equator is defined to have a declination of 0 degrees. So you might remember the lines of longitude and latitude on Earth. So the equator, this is a latitude of 30 degrees north, a latitude of 60 degrees north, a latitude of 90 degrees north. Here is the celestial sphere. There's the celestial equator. Declination is measured in the same way. An object on the celestial equator has a north-south position. We say a declination of 0 degrees. If the object is 30 degrees north of the equator, anywhere along this line, we say that it has a declination of 30 degrees north. Up here, we have a declination of 60 degrees north, and then finally up here, we have a declination of 90 degrees north. And we do the same thing in the southern hemisphere. This is 30 degrees south, 60 degrees south, and then 90 degrees south. So declination is simply how far north or south you are of the celestial equator. Just like latitude is how far north or south you are of the Earth's equator. Right ascension is your east-west position on the celestial sphere. And you'll remember that longitude on Earth is your east-west position on the Earth, and it is measured from some artificial, arbitrary location. You'll remember that in the case of longitude, we picked the observatory in Greenwich, England, as the beginning point for longitude. We did the same thing in the celestial sphere. We picked an arbitrary point and we called that a right ascension of 0. And the arbitrary point that we picked is actually really interesting because there's nothing there. It is the point where the sun crosses the equator, going from the southern hemisphere to the northern hemisphere on or around the spring equinox, which is on or around March 21st of every year. That day, the spring equinox, the sun crosses the equator, and that imaginary point in the sky where the sun crosses the equator, that is defined to be the 0 point of right ascension. Now, right ascension is a bit confusing because we don't measure it in degrees. We do measure longitude in degrees east or degrees west of the prime meridian. In the case of right ascension, we measure it in hours, minutes, and seconds of time with respect to this origin point of right ascension right there, with respect to the spring equinox. So how do we do this? Well, here's how we measure right ascension. Here's the spring equinox in the sky. And what we do to measure right ascension is we draw a line in the sky. Typically, astronomers use the meridian, which goes from due north to due south and passes straight overhead. And we watch when a star crosses that meridian. And what we do is we watch when the vernal equinox crosses that line in the sky. And when the vernal equinox, the spring equinox, crosses that line in the sky, we start a stopwatch. Sometime later, a star will go across that same line. And when that star goes across the same line, we look at the stopwatch, and the amount of time that has passed in hours, minutes, and seconds of time is the right ascension of that star. So let's take the bright star Vega. Vega is a bright star in the summer sky. It's high overhead right now. Vega is 38 degrees, 44 minutes north of the celestial equator. So if we start on the celestial equator, we would go north 38 degrees, 44 minutes, and we would find the bright star Vega. In terms of right ascension, there are 24 hours of right ascension. To go all the way around the sky, there are 24 hours. If we start at the vernal equinox, the right ascension of Vega is 18 hours, 35 minutes. Another way to put that is if I watch the sky, and the moment that the vernal equinox, the spring equinox, crosses that line, I start a stopwatch, the bright star Vega will cross that same line 18 hours, 35 minutes later. So we say that it has a right ascension of 18 hours, 35 minutes. Now, the reason I bring up right ascension and declination is we'll be using a robotic telescope this semester to observe the sky. And we have to know a little bit about right ascension and declination to determine where those objects are in the sky. So once you've started using the robotic telescope, hopefully this right ascension and declination will help you locate your objects in the sky. So to sum up today, to sum up this lecture, how an object moves through the sky depends not only on our latitude, but it also depends on its declination in the sky. So let's take this example right here at mid-northern latitudes. Here's an observer at a latitude of about 40 degrees north latitude. We're at 38 degrees here in Charlottesville, so that's pretty much our latitude on the surface of the Earth. There's their zenith, the point straight overhead. There is their horizon right there. And here are a variety of stars at different declinations. These stars have a declination of 0 degrees because they're right on the celestial equator. These have a declination of 30 degrees because they're 30 degrees north of the equator, 40 degrees north of the equator, 60 degrees north of the equator, and 90 degrees north of the equator at the north celestial pole. These stars are 30 degrees south and 60 degrees south. Oftentimes with declination, for the southern declinations, we put a minus sign in front of the numbers. Now, during the course of the day, as I said, you make this crazy rotation around the Earth right here. Your horizon makes this crazy coning motion. It's really hard to figure out. So let's go back to our celestial sphere, where we put ourselves standing straight up and down, and our horizon is horizontal. All we've really done is we've taken this diagram and we've tilted it over. When we do that, this is the path of the stars through the sky. The stars up here at very far northern declinations, at very high declinations, these are the circumpolar stars. They go round and round during the day, never rising or setting. Stars that are further south, for example, stars that have a declination of 30 or 40 degrees, they rise over here in the northeast, they make these big long paths, and they set over here in the northwest. A star that is right on the celestial equator rises exactly due east, moves across the sky, and sets over here exactly due west. An important thing to know about the stars is the only stars that rise exactly east are the same ones that set exactly west, and those are the stars on the celestial equator. Stars that are north of the equator rise in the northeast, move across the sky, and set in the northwest. Stars that are south of the equator rise in the southeast, move across the sky, and set in the southwest. So, those are the motions of stars through our sky. Now that we've seen that the declination of a star is a measure of how far north or south of the equator that the star is located, we can use that and combine it with our previous drawings of the celestial sphere to determine how high the star will get in our sky. So let's do this learning catalytics question. What is the maximum altitude above the southern horizon of a star at a declination 23 degrees north, as seen from Charlottesville, Virginia at 38 degrees north? Now there's a lot in this question, so let's start breaking it down a little bit. The first thing is it asks for a celestial sphere drawing at 38 degrees north. Then we'll figure out how high up the equator is, and then after that we will put the star on there and then figure out how high the star is. So let's go through all the steps that we did, and let's start by drawing our celestial sphere for an observer at 38 degrees north latitude. So you'll remember from our drawing our celestial spheres that the first thing that we do is we draw the Earth. Then we draw our observer standing on top of the Earth, standing straight up and down. Then we draw the celestial sphere around our observer. Then we label the observer's zenith. And we draw in their horizon. They can see everything above the horizon, and they can see nothing below the horizon. Then the next thing that we need to do is we need to orient the Earth underneath the observer. My observer is at 38 degrees north, and so as we've done many times, that will be the North Pole, that will be the South Pole, this will be the Earth's equator right there, and we extend this out to get the North Celestial Pole, the South Celestial Pole, and then finally the Celestial Equator. Now, what this question asks is it's not asking for how high up the pole is, and it's not asking for how high up the celestial equator is. It's asking about a star at a declination of 23 degrees north declination. Now, remember what declination means. It's how far north or south of the celestial equator you are. And to find a star at a declination of 23 degrees north, we start on the celestial equator, and we go 23 degrees north of the celestial equator. So if the celestial equator is right here, we go 23 degrees north of the equator, and that puts the star right here in the sky. So that is our star. And what I want to know is how high up that star is in the sky at its maximum altitude. Of course, the star rises in the east and sets in the west, but it reaches some maximum altitude, and I want to know how high up it is at its maximum. So how am I going to find that? Well, let's talk about the angles that we know. The first thing we know is how high up the North Celestial Pole is. And we know that because we are at a latitude of 38 degrees north. So we know that this angle right here is 38 degrees. That is the height of the North Pole above the northern horizon is 38 degrees. The other angle that we know is how far it is from the North Pole to the equator. And that is always going to be 90 degrees wherever you are on Earth. And that means that this angle right here, how high up the equator is in the sky, has to be 180 minus 90 minus 38, which is equal to 52 degrees up in the sky. So this angle right here is 52 degrees. And what that tells me is that the celestial equator is 52 degrees above the southern horizon right there. But that's not the answer I'm looking for. That's how high up the equator is. The star is another 23 degrees beyond that. So to get the altitude of the star, I have to add the 52 and the 23 together, and I get 52 plus 23 is equal to 75 degrees. That is, that star gets 75 degrees above the horizon at its highest. So the key to answering questions like this is to remember that the declination of a star, how far north or south it is with respect to the equator, is always indexed to the celestial equator. So the first thing we need to do is use our latitude to figure out how high the pole is, use that to figure out how high the equator is, and from that we can figure out how high the star is. Let's do another example. Let's do this example. Now, it looks almost the same. In fact, if you weren't watching carefully, you probably didn't even notice the text change, but there's a little change in the text right there, which is, what is the maximum altitude above the southern horizon of a star at a declination 23 degrees south as seen from Charlottesville, Virginia? So let's go ahead and answer this question. Okay. So for a star, the first thing we need to do is we need to draw our celestial sphere. So to draw our celestial sphere, we will draw that for someone at 38 degrees north latitude. We will do exactly what we did before. Our location on Earth hasn't changed, and so we're still going to be drawing a celestial sphere for someone at 38 degrees north. So we will draw the Earth. We will draw our observer standing on top of the Earth. We will draw the celestial sphere around our observer. We will label their zenith. We will draw in their horizon. We will orient the Earth underneath them, so that is their north pole, their south pole, the equator, and extend those out to get the north celestial pole, the south celestial pole, and the celestial equator. So the question, where is the star this time? Well, the star is at a declination of 23 degrees south. So now we start on the equator and we have to head towards the South Pole. So we go about 23 degrees south, and that's going to put the star right about there in the sky. And what I want to know is its maximum altitude. I want to know how high up in the sky that star gets. So we need to figure out how high up that star will get. So let's go back to the angles we know. The first angle that we know, of course, is that this angle is 38 degrees. That is the height of the pole in the sky. We know that the angle from the pole to the equator is 90 degrees. And that means this angle right here is 52 degrees. That's how high up the celestial equator is in Charlottesville. It's not true everywhere, but that's true in Charlottesville. Now, again, that's not our answer. That's how high up the equator is. But the star is now south of the equator, so it is 23 degrees south of that. So this angle is 23 degrees, which means that this angle, the remaining angle here, must be 52 degrees minus 23 degrees, which is 29 degrees. So the altitude of the star here is 29 degrees. With this formula, or with this idea of drawing this two-dimensional celestial sphere, we can figure out the maximum altitude of any star for anywhere on Earth. So long as we know our latitude on Earth and we know the declination of the star, we can figure out how high it will get at its maximum altitude during the day. And I want to emphasize this is the maximum altitude. The star, of course, rises over here in the east, moves across the sky, gets to its maximum altitude, and then it goes and it sets on the other side of the sky. But this is the maximum altitude. That is how high up it gets at its highest during the day. So now that we've done two of these problems, let's go ahead and pick up and see more about how the sky looks and rotates at different latitudes. Okay, let's take a look now at how the sky changes when we view it from a couple different latitudes. And let's start with how it would look from the poles. So this is for an observer standing on the north pole of the Earth, and we'll see it in two separate cases. Here at the top is a celestial sphere. So we've got the Earth with the observer standing on top of the North Pole. As the Earth turns from west to east, everything in the sky looks like it's going east to west. And these are how the stars move in the observer sky. Down here on the bottom, we see the same thing, but with a close-up of the observer showing their horizon, so they can't see anything below the horizon down here, but they can see everything above the horizon. If you're standing on the North Pole, the stars make circles through the sky, and they never get any higher or lower. They never rise or set. They just circle round and round the sky forever. So a star at a declination of 60 degrees north, that is a star that is 60 degrees north of the equator, will make this circle in the sky and just go round and round. A star that is 30 degrees north will make this circle round and round. And a star at a declination of 0 degrees, one that is right on the celestial equator, will be right on the observer's horizon and will go right around the horizon. So here they are again down here. Here is that star at a declination of 0 degrees going right around the horizon. So what's interesting about standing as an observer at the North Pole of the Earth is that no stars rise or set at the North Pole. All of the stars that you can see in the northern sky are circumpolar. They go around the pole. You can see none of the stars in the southern hemisphere. You can see none of the stars that are south of the celestial equator. They are eternally hidden from view. And then the other thing that's amazing about the North Pole is that the stars just make these circles that go round and round. Now, we will learn during the seasons that the North Pole gets 6 months with daylight and 6 months with continuous nighttime. When it is daytime and the sun is up, of course, you can't see the stars going round and round. But when it is nighttime and the sun is below the horizon, you do see the stars circling around. Now that we've seen what the sky looks like from the pole, let's look at the sky from the equator, the Earth's equator. This is a celestial sphere drawn on the left for an observer who's standing on the equator of the Earth. And again, as the Earth turns from west to east, it looks to them like the sky is turning from east to west. It looks to them like the sky is going around in this direction. Now, because the sky is turning around the north and south celestial poles, the whole sphere is turning around the poles there, these are the paths of the stars. The stars rise out of the east, move across the sky, and set in the west. Now again, it's really hard to picture what's going on here because our observer is not straight up and down. Our observer is tilted over sideways. So let's look at what it looks like when we now orient this so that our observer is straight up and down. For someone standing on the Earth's equator, the North Pole is on their northern horizon, literally right on their horizon. The South Pole is on their southern horizon. And the celestial equator goes from due east to straight overhead to due west. So this is the celestial equator in the sky. And what happens living on the equator is that all the stars rise they rise in the east, they move across the sky, and they set in the west. And where they rise depends on their declination. A star that is right on the celestial equator, that has a declination of 0 degrees, will rise exactly due east, move through the sky, go straight overhead, and then set exactly due west. A star that is 30 degrees north of the celestial equator will rise in the northeast, move across the sky, and set in the northwest. And a star that is 60 degrees north of the equator, at a declination of 60 degrees north, will rise very far in the northeast, not get very high, and set very far in the northwest. The opposite is true of stars in the southern sky. A star that is 30 degrees south of the equator, at a declination of minus 30 or 30 south, will rise in the southeast, get fairly high in the sky, and set in the southwest. And a star that is a declination of minus 60 degrees will rise in the very far southeast, make this little arc across the sky, and set in the southwest. What's interesting about all of these arcs is you'll notice that the horizon cuts all of them equally in half. That is, this star spends half of its day above the horizon and half of a day below the horizon. That is, this star spends 12 hours in the sky and 12 hours below the ground. This star, its path is cut in half as well. It spends 12 hours in the sky and 12 hours below the ground. And this star spends 12 hours in the sky and 12 hours below the ground. If you live at the equator, all stars are in the sky for exactly 12 hours and they're below the horizon for exactly 12 hours. And you can see maybe on the left why that is, and that's because the observer's horizon, which is vertical in this case, is cutting the celestial sphere perfectly in half. So these are two interesting case studies. The pole, where nothing ever rises or sets, and the stars are up continuously 24 hours a day forever. And living on the equator, where the stars are up for exactly 12 hours, but every star is up for 12 hours. None of them are up continuously. And now think about both of those and compare them to the situation that we have here in Charlottesville at mid-northern latitudes. And by mid-northern latitudes, I mean pretty much anywhere in the continental United States. So here is somebody that is living at 40 degrees north latitude. That's pretty close to where we live here in Charlottesville. It's a nice middle latitude that cuts right across the middle of the United States. And so if you live in the continental United States, seeing how the sky looks like from 40 degrees is a pretty good estimate of what it's going to look like pretty much anywhere in the continental U.S. So here's the observer. That's the zenith, the point straight overhead. This is their horizon right here. And these are the paths of the stars. These stars are up continuously. As the Earth turns and the stars circle around the pole, this star is a circumpolar star. It never sets. These stars rise in the east, move across the sky, and set over here in the west. And because both of these are north of the equator, they rise in the northeast, move across the sky, and set in the northwest. Here's a star on the celestial equator. Rises due east, moves across the sky, and sets due west. This star makes a little tiny arc in the sky, and then these stars down here are the ones that are very far south that never rise up. Again, this diagram is confusing because the observer is tilted. Let's go over here and look at the observer standing straight up and down. Really, all we're doing is we're taking this and we're tilting it over a little bit till our observer is standing straight up and down. And here's what the sky looks like to them. They see up there in the sky the north celestial pole. And the north celestial pole is not straight overhead. It's not down on the horizon. It's not straight overhead like it is at the North Pole. It's not down on the horizon like it is at the equator. It's about halfway up in the sky, a little less than halfway up in the sky. And in fact, because they're at a latitude of 40 degrees, it is precisely 40 degrees up in the sky. So the north celestial pole is about halfway up in the sky. The stars rise somewhere over here in the east, move across the sky, and set in the west. Stars on the celestial equator, that is, stars with a declination of 0 degrees, rise exactly due east. They move across the sky and they set exactly due west. And as we've already seen, at our latitude, the celestial equator at 38 degrees latitude gets all the way up to an altitude here of 52 degrees. In this case, where we're at a latitude of 40 degrees, they get up to an altitude of 50 degrees right there. Stars that are north of the equator rise in the northeast, move across the sky, and set in the northwest. Stars that are south of the celestial equator rise in the southeast, move across the sky, and set in the southwest. And then finally, stars that are very far north of the equator, in fact, stars that are within 38 degrees of the pole here in Charlottesville, or within 40 degrees of the pole for this observer at a latitude of 40 degrees, stars that are close enough to the pole that they never rise or set are the circumpolar stars. And so these are the stars that are circumpolar. They go round and round and never rise or set. And these, of course, are the stars that are within, in this case, within 40 degrees of the south celestial pole. These stars never rise up. They're never visible at our latitudes. Now, we've spent a lot of time talking about how stars at different declinations move through the sky. And you might wonder why I've spent so much time on this. And there's an interesting reason why. And this is a good time of the year to talk about it. You've probably noticed that the days, as the seasons go on, get longer and shorter. And the question is, why do the days get longer and shorter? You've known this happens your whole life. You know that the days in the summer are longer and the days in the winter are shorter. But I would bet that most people could not produce a scientific explanation for why that is. Why are the days longer in the summer? Why are the days shorter in the winter? It turns out understanding this is crucial to a scientific understanding of our seasons. So let's take this celestial sphere for a second, and let's ask a learning catalytics question about it, which is not how high do the stars get at all these different declinations, but how long do they spend in our sky? That is, how long are they above the horizon? So I want you to go to Learning Catalytics and I want you to answer this question. As seen from Charlottesville, how many hours will a star on the equator of declination 0 spend above the horizon? To help you out here, this is a star on the celestial equator. How many hours a day will it spend above the horizon? And remember, to go from here all the way around the circle back to here again is 1 day or 24 hours. So it takes a star 24 hours to go all the way around the circle and come back again. To answer how many hours it's going to be above the horizon, what you have to do is compare the size of this arc to the size of that arc. Because this arc is when it's above the horizon, and this arc is when it's below the horizon. So compare those two and determine which of these answers is best. Take a few seconds, go to Learning Catalytics and answer the question. How many hours a day will a star on the equator spend above the horizon? Okay, now that you've answered that question in Learning Catalytics, let's study what the answer is. I have to say, when I look at this arc right here, and I look at that arc below the horizon, the two of them look to be the same size to me. It looks to me, in fact, that the Earth's horizon is cutting this circle exactly in half. And that is exactly what happens. When a star is on the celestial equator, it spends 12 hours above the horizon and 12 hours below the horizon. It spends the same time in the sky as it does below the sky down there. So, a star on the celestial equator, one with a declination of 0 degrees, spends 12 hours above the horizon. Now I want you to answer this question for a star at a declination of 40 degrees north. So for this star right here at a declination of 40 degrees, it rises way over here in the northeast, makes this huge big arc through the sky and sets way over here in the northwest, and then makes this little tiny arc underneath the ground right there. Of these choices right here, which one best describes the number of hours that that star spends above the horizon? So go ahead, answer the question in Learning Catalytics. I'll wait. Okay, what did you think of this one? So let me reason it out. When I look at a star, when I look at the path of a star that is a declination of 40 degrees north, it looks to me like it spends a lot more time above the horizon than it does below the horizon. In fact, it seems to spend, it looks to me to be probably 3/4 of the day above the horizon and maybe 1/4 of the day below the horizon. It's definitely spending more than 12 hours above the horizon because this arc is much, much bigger than the one below the horizon. And so the answer is definitely bigger than 12 hours. But the other thing I know is that it's not 24 hours because this star does set and it does spend some time below the horizon down here. So this star is definitely not up for a continuous 24 hours. And of the choices that I gave you, by far the best answer here is 18 hours. So a star at a declination of 40 degrees north spends 18 hours above the horizon. And then finally, let's talk about this one. How about a star at a declination of minus 60 degrees? So a star at minus 60 degrees is down here. How many hours a day does it spend above our horizon as seen at mid-northern latitudes here? So go ahead and take a minute to answer that question. Okay, hopefully this one was fairly easy to come up with an answer. You notice that a star down here at a declination of minus 60 degrees goes round and round in the southern sky. It never, ever peaks above the horizon. And so it is above our horizon for 0 hours every day. It never rises up. So now what we've seen is that these stars are up all the time. They never set. These stars are up for more than 12 hours. Stars that are on the celestial equator are up for exactly 12 hours. Stars that are south of the celestial equator, like this one, they only spend 6 or 8 hours in the sky, and then they spend down here sort of 16 to 18 hours below the horizon. Let's look at this star at a declination of minus 30. It rises down here in the southeast, it sets in the southwest, and it makes this little tiny arc across the sky. It spends far more time below the horizon than it does above the horizon, which means this star is in our sky for only about, in this case, 9 hours a day, and it's below the horizon down here for about 15 hours a day for that star at a declination of minus 30. So to summarize, and this is probably the most important thing to realize about the movement of the sky, and this is a good figure to come back to and spend some time studying this figure. The stars that are very far north, the stars that are within, here in Charlottesville, that are within 38 degrees of the pole, these are the circumpolar stars. They're always above the horizon. They never set. Stars that are north of the equator, but south of the circumpolar stars, that is, these stars at intermediate latitudes here, or intermediate declinations, these stars are up for more than half a day. A star on the celestial equator is up for exactly half a day. A star that is south of the equator is up for less than half a day, and if we go far enough south, the stars never rise. This is giving us a hint as to why the length of the day changes during the seasons. As we're going to find out in our next lecture when we study the seasons, or the lecture after that, our sun is not sitting still in the sky. Our sun wanders north and south of the equator. And when the sun is north of the equator, it's up for more than 12 hours. When it's on the equator, on 2 special days of the year that we call the equinox, it's up for exactly 12 hours. And when our sun is south of the equator, it spends less than 12 hours in the sky. That is why the length of our day changes. But you'll have to see why the sun, in order to see why the sun is moving north and south of the equator, you're going to have to join me in the next 2 lectures, lectures 7 and 8. In lecture 7, we're going to talk about some common ideas about what causes the seasons. And then in lecture 8, we will build up a scientific understanding of what causes the seasons on Earth. So thank you for joining me in this lecture. I will see you in lecture 7.